All right, moving into section 11.3 now. This one should be quick, and it should be stuff that you all have seen before. So we're looking at polar coordinates. This should just be an introduction to polar coordinates, and it's going to be kind of a crash course here. So just quick definition. So first thing we're going to do is we're going to fix an origin, which we're going to label with a capital O. This origin is the same origin that we normally get for our coordinate plane. We also need to look at an initial ray from this origin. So a ray is just a line that has an arrow attached only to one end. So it has a fixed initial point, but then it goes forever in one direction. So if we have these two things, an origin and an initial ray, this initial ray that we're talking about is going to be the positive x-axis. You'll kind of see that here in a second. Then each point P can be located by a polar coordinate, where this polar coordinate is in the form r theta. Sorry, I have to be in the equation editor thing. There we go. So the form r theta here, where this r that we're talking about, this is going to be the distance from that origin point. And then the theta that we're talking about, this is going to be what we call the direction angle, but you can also think of it as the angle in standard position. Okay, just a little bit more about this. This theta that we're talking about is always positive. Well, I guess it doesn't always have to be positive, sorry. If it is positive, that means that we're going counterclockwise. And then one thing about that is that with this angle, it is not unique. So that's kind of a problem with polar coordinates. I don't know if problem is the right word here, but that is why rectangular coordinates, the one that we always use, x's and y's, are the most often used. It's the most often used because it's a one-to-one relationship. Every single point corresponds to only one ordered pair, and every ordered pair only corresponds to one point. We do not have that with polar coordinates. And so I opened up Desmos here just to show you a couple of examples. So I graphed 2 points for us. We have the point 2 pi over 6, so just to see how that point works. Here we have a polar grid. The positive x-axis is that initial ray that we're talking about. Origin is still the origin of the xy axis, the intersection of those two things. The point 2 pi over 6 is 2 units away from the origin, and it's at this angle pi over 6 and the normal position here. Just as another example, here we have the point 211 pi over 6, this blue one down here. Same distance away from the origin, but now this is at the positive angle 11 pi over 6. If I wanted to define another point that gives us the same value here, if I define the point 2 negative 11 pi over 6, notice that that gives me the same exact point as the red 2 pi over 6. So 2 pi over 6 and 211 pi over 6 are the exact same point. So you can define the same point using different ordered pairs. Okay. A couple other things that I want to say to remind you a little bit about polar coordinates is that we can have polar equations and then the graphs of these polar equations. We're only going to look at a few of these, so just a couple basic examples. Let's just look at the equation r equals 1. If we're looking at the equation r equals 1, Desmos can graph this for us as well. Notice that all we get is the circle. This is the circle that has a radius of 1, r equals 1. Okay. Another example, so this was circle at the origin, or with center at the origin with radius 1. Another example, just maybe a little bit more complicated. This one I cannot graph in Desmos for whatever reason, but if I have theta is equal to pi over 6, just to go over to the graph here in Desmos, theta equals pi over 6 is going to be a straight line. It's always a straight line that goes through the origin, and then this is going to be the straight line that goes through the angle pi over 6 forever in the forward direction and the backward direction. So just imagine that this gray line here is filled in from pi over 6 even back to the angle 7 pi over 6 forever and ever and ever. Okay, and then you'll have a little bit more involved examples. So let's say that you're given like an inequality. 1 is less than or equal to r is less than or equal to 2, and 0 is less than or equal to theta is less than or equal to pi over 2. Okay, so this would be an inequality, right? So we're shading in the graph. Again, if I go over to Desmos, Desmos was kind of freaking out on me a little bit when it came to these inequalities, so here's my best shot at it. I'd have to graph these separately. So here's the first part of that inequality. R is greater than or equal to 1, and I only care about this between 0 and pi over 2. So notice that I'm shading in this region where my R values are greater than 1, but only between the angles 0 and pi over 2. Separately, if I shade the other part of that inequality, R is less than or equal to 2 on that same interval, I get this purple region. What we care about from our example here, 1 less than or equal to r less than or equal to 2, and then 0 less than or equal to theta less than or equal to pi over 2, is where my purple and my green intersect. So notice that we get this kind of arc-looking shape here. This has a name to it. This is what we call a polar rectangle. So this is a polar rectangle here, defined like this. 1 less than or equal to r less than or equal to 2, 0 less than or equal to theta less than or equal to pi over 2. Okay. A little bit more about this. This should just be a reminder here. There are 4 equations that let us give back and forth between polar and rectangular coordinates. So these are equations relating polar to Cartesian. All right, so the 4 equations are x is equal to r cosine theta, y is equal to r sine theta. All right, so these are the equations that you want to use whenever you're going from polar coordinates to rectangular coordinates. If you have the r and the theta ordered pair, you just plug them into these 2 equations to get the x and the y. Now, if you have the x and the y and you want to find the polar equation, you would use these 2 equations. R squared is equal to x squared plus y squared. That's just coming from the Pythagorean theorem. And then the other one, tangent of theta, is equal to y over x. This one's a little bit more difficult to do. You have to know which quadrant your point is in so that you know which angle to use in tangent of theta. But they're not too hard. The way that we are going to use them is that we are going to be looking at converting equations over and not necessarily points. Something like find a polar equation for the circle x squared plus y minus 3 squared is equal to 9. Okay, so we can graph this in Desmos again. X squared plus y minus 3 squared is equal to 9. Let me just get rid of some of this stuff. Oops. Okay, so x squared plus y minus 3 squared is equal to 9. All right, so we get this circle. Okay, I know I'm still in the polar grid here, but that's all right. This is going to be the circle that has a radius of 3, and it has a center at x equals 0, y equals positive 3. Think of that like the translations you saw back in 171. So here the center is at the point 0, 3, and it has a radius of 3. It goes up to 6, down to 0, and it goes left and right 3. Okay, let's look at taking this equation but converting it over to polar form. So if I wanted to convert this over to polar form, I want to get rid of the x's and the y's, and I only want r's and thetas left over. We're using these equations up top. Notice that these 2 equations up top here are not going to be super helpful yet. You could, of course, just plug them in. Let x be r cosine theta, and then you're going to have that squared. Let the y be r sine theta, and then that'll be minus 3 all squared. And that does work, but there's better ways of doing it. The better way of doing it is going to be to multiply this all out. So we'll leave the x squared, but we're going to FOIL out the y minus 3. So we'll have y squared minus 6y plus 9 is all equal to 9. Subtracting the 9 from both sides. Okay, now that x squared plus y squared out in front, that is the right-hand side of this equation. So I can just replace x squared plus y squared with this r squared. This lone y that we have on the -6, there's not too much we can do with that except for replace it with this equation, the r sine theta. So this will be my equation here. The x squared plus y squared is changing into r squared. I still have the -6, and then my y I'm going to rewrite as r sine of theta. And that's all still equal to 0. Okay, and then even this we could take a little bit further, right? Because what I could do is I could factor. If I factor out an r, I have this, right? R times r minus 6 sine theta is equal to 0. And then I could set these two things equal to 0 separately. So I'll have r is equal to 0, and then I'll have r minus 6 sine of theta is equal to 0. This first equation is nothing. R equals 0 is just going to be the origin point. It's kind of the case that nobody cares about. This, though, is a little bit more interesting. If I add that 6 sine theta over to the other side, I get this. R is equal to 6 sine theta. Notice how much better this equation looks compared to what we started with. Just to double check to make sure it works, here, if I define R to be 6 sine of theta, notice that my red line that I'm getting is intersecting, completely tracing over the black line there. So they really are the exact same equation, one of them in Cartesian form, one of them in polar form. We can do the same thing, but the other way around. So just another example. Instead of me giving you something in Cartesian form and asking you to change to polar, I could give you something in polar and ask you to change to Cartesian. So if we had something like r squared is equal to 4r cosine of theta. And the question would be change to Cartesian form. All right, so to do that, we're doing the same thing. We're just replacing r and theta with x's and y's using these 4 equations up top here. So going back down, I have r squared, and then I have this r cosine theta multiplied on the 4. So just replace it, right? R squared, remember I can replace that with x squared plus y squared. I still have the 4 there on the right-hand side, and then r cosine theta changes directly into x. And then that's not really too much that we could do here. We could fiddle with this a little bit, but I just want to do a quick little example. As long as you have the r's and the thetas gone with just x's and y's left over, you can just stop there and you're good. I promise that the homeworks will count it right as long as the r's and the thetas are gone.